Quantum entanglement is one of the most mysterious phenomena in existence. Quantum entanglement seems to indicate that messages can be sent from one particle to another instantaneously, even if the two particles are located on opposite sides of the universe. However, according to Einstein's theory of relativity, no information can ever travel faster than the speed of light. According to Einstein's theory of relativity, if a message could travel faster than the speed of light, then it would be possible to send messages backwards in time. Yet, quantum messages traveling instantaneously can seem to be demonstrated by measuring the polarization of two entangled photons, or by measuring the spins of two entangled particles, such as an electron and a positron. The principle for quantum entanglement is the same in both cases, but in this video, we will just focus on measuring the spins of particles such as electrons and positrons, and the polarization of photons will be discussed in a separate video. In classical physics, the spin of a particle can be represented by an arrow pointing along the axis of rotation. Particles spinning in opposite directions have their arrows pointed in opposite directions. We have the ability to measure the spin of the particles with a detector. But in quantum physics, the detectors always provide us with only one of two measurements, which is either towards the red plate or towards the blue plate. Therefore, depending on how we orient the detectors, we can measure the spin in only one direction at a time. We have the ability to produce pairs of particles, which we refer to as an entangled pair. We can measure each of these particles with a separate detector. If we align the two detectors in the same direction, then the spins of the two particles will always be in the opposite directions 100% of the time. This is predicted by both classical physics and by quantum mechanics. If the two detectors are aligned 90 degrees to each other, the two particles measure opposite spins exactly 50% of the time. This is also predicted by both classical physics and by quantum mechanics. But if the two detectors are aligned somewhere in between these two directions, then quantum mechanics gives a very different prediction than does classical physics. According to classical physics, the angle of the two detectors should have a linear relationship to what percentage of time the two particles have spins in opposite directions. But according to quantum mechanics, this relationship is a sine wave. When we actually perform the experiment, the result we get is always the one predicted by quantum mechanics, and not the one predicted by classical physics. Suppose we align the two detectors 45 degrees to each other. Classical physics predicts that the two particles should have opposite spins 75% of the time. But quantum mechanics predicts that the two particles should have opposite spins approximately 85% of the time. And it is this 85% which is actually measured. However, the fact that we measure 85% instead of 75% implies an inherent logical contradiction. leading us to believe that the two particles are sending messages to each other instantaneously, with all the inherent implications about messages traveling backwards in time. In order to understand why this is the case, let us first consider a simple logical thought experiment that is not related to quantum mechanics or to this experiment with the measurement of spins. Suppose we have a collection of marbles. Each marble has three properties that we will call X, Y, and D. For each marble, we are allowed to choose only one of these three properties to measure. Each of these properties can have only one of two values, which we will call red and blue. That is, the X property of each marble can be either red or blue. The Y property of each marble can be either red or blue. And the D property of each marble can be either red or blue. Suppose that all the marbles are arranged in groups of two. That is, each marble is partnered with one other marble. Each marble is separated from its partner, and the two marbles are placed on opposite sides of the universe. We now choose one of the three properties to measure for each of the marbles. If we choose the same property to measure for both a marble and its partner, then we always get the same outcome for the two marbles. That is, the X property of the two marbles either both come out red or they both come out blue. The Y property of the two marbles either both come out red or they both come out blue. And the D property of the two marbles either both come out red or they come out blue. Now suppose we choose different properties to measure for a particle and its partner. If we measure the D property of one of the marbles, and we measure the X property of its partner, they both always have the same value. And if we measure the D property of one of the marbles, and we measure the Y property of its partner, they again both always have the same value. Now, what if we measure the X property of one of the marbles, and we measure the Y property of its partner? Based on the information presented so far, we should expect that they too should always have the same result. What if we were told that this is not the case, and that they have the same value only 50% of the time? This would seem to be a logical contradiction with the information we have been presented. If D is always the same value as both X and Y, then X and Y must always be the same value as each other. But what if when we actually performed the experiment, X and Y were in fact equal to each other only for 50% of the pairs of particles? This would imply that there is something fundamentally wrong with the rules of logic as we understand them. Now let us consider a slightly different scenario. Again, suppose that we have a collection of marbles, and each marble is again partnered with one other marble, as described previously. As before, each marble has three properties, which we will call X, Y, and D. And it is possible to select only one of these three parameters to measure for each marble. As before, if we choose the same property to measure for both a marble and its partner, then we always get the same outcome for the two marbles 100% of the time. But this time, if we measure the D property of one of the marbles, and we measure one of the two other properties of its partner, they have the same measurement 85% of the time. That is, if one of the marbles has red for its D parameter, then its partner has red for its X parameter 85% of the time. And if one of the marbles has red for its D parameter, then its partner has red for its Y parameter 85% of the time. If X is different from D 15% of the time, and D is different from Y 15% of the time, then X and Y can be different from each other only 15% plus 15% of the time, which is a maximum of 30%. If one of the marbles in each pair has red for its D parameter, then we can have any one of the following situations shown. If one of the marbles in each pair has blue for its D parameter, then we can have any one of the following situations shown. Now, let's take a marble and its partner and measure the X parameter for one marble and measure the Y parameter for its partner. Based on the information that has been provided, what should we expect? If X is different from D 15% of the time, and D is different from Y 15% of the time, then X and Y can be different from each other only 15% plus 15% of the time, which is a maximum of 30%. The answer, therefore, is that X and Y values should be the same between 70% and 100% of the time. what if we were told that this is not the case and that they have the same value only 50% of the time? As before, this would seem to be a logical contradiction with the information we have been presented. Based on the information provided, the x and y values must be the same at least 70% of the time, and not less than this. But what if when we actually performed the experiment, x and y were, in fact, equal to each other only for 50% of the pairs of particles? This would again imply that there is something fundamentally wrong with the rules of logic as we understand them. Now let us consider yet another scenario. This new scenario is identical to the previous example, but in this case we take one of the two marbles out of each pair, and we reverse the values of all of its three parameters, x, d, and y. This means, if we choose the same property to measure for both a marble and its partner, then we now always get the opposite outcome for the two marbles 100% of the time. And each marble will have d values opposite from the x value of its partners 85% of the time. And each marble will have d values opposite from the y value of its partners 85% of the time. In this case, if we are asked how often the x value from one marble will compare to the y value of its partner, the analysis for this is identical to the previous scenario, but in reverse. The logical answer should be that the two values must be opposite between 70 and 100% of the time. But what if when we actually performed the experiment, x and y were in fact opposite to each other for only 50% of the pairs of particles? This would again imply that there is something fundamentally wrong with the rules of logic as we understand them. This last scenario is precisely the situation that we actually have with measuring the quantum spins of entangled particles. For example, we have the ability to produce pairs of particles that each have three different properties that can be measured, which we call the x direction of spin, the y direction of spin, and the diagonal direction of spin. The relationships between these three measurements is identical to the one described in the last scenario, and we actually do get the 50% relationship between the x and y parameters when we perform the experiment. Though this 50% figure is not what is mysterious, as 50% is exactly what we would have expected from classical physics before quantum mechanics was discovered. What is mysterious is the 85% relationship between the diagonal direction of spin and the other two measurements. In classical physics, this relationship is 75%. A 75% relationship between the diagonal direction of spin and the other two measurements is logically consistent with a 50% relationship between the x and y directions of spin. However, as discussed above, an 85% relationship with the diagonal direction of spin is not logically consistent with the 50% relationship between the x and y directions of spin. Yet this 85% relationship is what is predicted by quantum mechanics, and this 85% relationship is what is actually measured. This logical contradiction is exactly equivalent in all of the three scenarios that have been discussed. It is only the third scenario that actually occurs in quantum mechanics. But in order to try to figure out how to resolve the logical contradiction in the scenario that actually occurs in quantum mechanics, let us go back to the first scenario, as this is the scenario which is the easiest to think about. Whatever solution we come up with for resolving the logical contradiction in the first scenario will also apply to resolving the logical contradiction in the scenario which we actually observe in quantum mechanics. To review, in the first scenario, if we choose the same property to measure for both a marble and its partner, then we always get the same outcome for the two marbles. And if we measure the D property of one of the marbles, and we measure the X property of its partner, they both always have the same value. And if we measure the D property of one of the marbles, and we measure the Y property of its partner, they again both always have the same value. Based on this information, we therefore expected that if we measured the X property of one marble and the Y property of its partner, we would also always get the same value. But we were told that this is not the case, and that they were the same only 50% of the time. Where did we go wrong with our logic? One possibility is that we made an error when we assumed the three parameters inside each marble are always either red or blue, even when we are not observing them. Suppose that each parameter becomes either red or blue only at the moment when we measure it, and that there is no way to predict the measurement ahead of time. This would mean that even after we measure the X parameter, the y parameter of the marble is still neither red nor blue, due to the fact that y has not been measured, and we can never measure both the x and the y parameter for the same marble. This would explain why we should have no reason to expect the x parameter of a marble to be equal to the y parameter of its partner, in spite of the fact that the d parameter of a marble is always measured to be equal to both the x and the y parameter of its partner. This solves the logical contradiction, but this now presents a new problem. If it were somehow possible to predict the measurements of x, y, and d properties of a marble before the measurement is performed, then for the purpose of this analysis, this would be logically equivalent to each of these properties already having a value of either red or blue even before the measurement is performed. In this case, our explanation for why the x property of a marble is not always equal to the y property of its partner will not work. For example, suppose that we can predict ahead of time that the x property of the left marble will be red. This would mean that we would be able to also predict ahead of time that the x property of the right marble will also be red, due to the fact that the two marbles always have the same value for the same property. Once we know that the x property of the right marble will be red, we will also be able to predict that the d property of the left marble will be red, due to the fact that the d property of a marble is always equal to both the x and y properties of its partner. For these same reasons, once we know that the d property of the left marble will be red, then we will also be able to predict that both the d and y properties of the right marble will be red. And once we are able to predict that the y property of the right marble will be red, we can now predict that the y property of the left marble will be red. And hence, we again end up with the logical implication that the x parameter of one marble must always be the same as the y parameter of its partner, which is in direct contradiction to what we actually observe. Therefore, the only way our explanation for this contradiction can work is if there is no way for anyone to be able to predict ahead of time whether a parameter of a marble will be red or blue until someone actually performs a measurement. But let us consider what happens when we perform a measurement on only one of the two marbles. If we measure that the x parameter on the left marble is red, then we will automatically know in advance that the x parameter of the right marble must also be measured red, due to the fact that the x parameters of the two marbles are always measured to be the same value. Therefore, the moment we measure that the x parameter of the left marble is red, the future x measurement of the right marble instantaneously changes from being neither red nor blue to being 100% red. This seems to imply that the moment the x parameter of the left marble is measured to be red, it sends an instantaneous message to the right marble, letting it know that its x parameter must also be red. But what would the implications of such an instantaneous message be for Einstein's theory of relativity? According to Einstein's theory of relativity, different observers can disagree about which of two events happened first, and both points of view are equally valid. Suppose a message is sent from point A to point B. So long as the message travels slower than the speed of light, then all observers will agree that the message will arrive at point B after it is sent from point A. But if the message travels faster than the speed of light, then from the perspective of some observers, the message will arrive at point B before it was sent from point A. In other words, the message was sent backwards in time. If it is possible to send information backwards in time, this would create many logical contradictions. For example, it would be possible to win the lottery by sending the winning lottery numbers backwards in time, thereby changing the events that have already occurred in the past. However, if we consider the messages in our thought experiment with the marbles, we should realize that sending these messages backwards in time does not create any logical contradictions. This is due to the fact that the only messages that are sent are whether one of the parameters is red or blue, and this is a completely random outcome which we have no control over. Since we have no control over the contents of the message that is sent, we would never be able to use these messages to encode useful information, such as the winning lottery numbers. We would therefore not be able to use these messages to change past events that have already occurred, and therefore no logical contradictions have been created. We could also therefore say that Einstein's theory of relativity has not been violated, because this theory only states that information can never travel faster than the speed of light, and that these random messages that we have no control over do not count as information. The two different observers in our experiment would simply disagree on which of the two marbles was measured first. From one observer's perspective, the X parameter of the left marble was measured first, and the left marble sent an instantaneous message to the right marble to let it know what its X parameter needed to be. From another observer's perspective, the X parameter of the right marble was measured first, and the right marble sent an instantaneous message to the left marble. Both points of view would be equally valid, and this would not create any logical contradictions. Everything in this analysis also applies to the scenario that we actually observe in quantum mechanics, where the two entangled particles always have opposite spins in the same direction, have opposite spins 85% of the time when the detectors are aligned 45 degrees apart, and have opposite spins 50% of the time when the detectors are aligned 90 degrees apart. This is what leads us to believe that the spin of a particle does not actually have a direction when we are not observing it, and that the particle makes up its mind only at the moment it is measured, with no way to predict the outcome ahead of time. As before, this also implies that each time the spin of a particle is measured, It sends an instantaneous message letting its entangled partner know that it must spin in the opposite direction if the two detectors are aligned at the same angle. And this all has the exact same implications for Einstein's theory of relativity and sending messages backwards in time that was discussed previously. Much more detailed information about both quantum mechanics and Einstein's theory of relativity are available in the other videos on this channel. Please subscribe for notifications when new videos are ready.